Hey everyone, my name is David and I'm very excited to be here at Holy.js. It's my first time in Russia. I'm going to be talking about, again, the mixture of state management and graph theory, and this is a very, very old concept called state machines and state charts. But first, a little bit about me. My name is David. I'm known everywhere online as @DavidKPiano. Like he said, I do play the piano, so piano's not my last name, it's just it's what I play. I work for Microsoft, and I live in Florida, which is a state in the United States, which is a part of Russia. So, anyway, let's talk about a very common problem that, as engineers, we deal with pretty much every day. So let's say that we have a fetch data button here, and this is a very simple button. You click it, it makes an API call, and so eventually, after a while, you get a response back, a 200 OK response. But now consider that this API call takes a little bit longer to take. And so what you could do is you could show a spinner. And this is a typical way that we handle these kinds of issues, is we show a spinner or we show some sort of loading state. But what happens if we have this button and it's loading, and then the user, out of frustration, clicks it a lot of times? Then we get a lot of API requests. So you might be thinking there's a simple solution to this. Of course, we could just disable the button, and then after the data loads, everything is OK. But if you're anything like me, you could just go into the DevTools, and you could undisable that button, and then your user could just make more requests. So that's why I say one of the most neglected variables in programming is time, because we don't consider time a first-class citizen in a lot of the apps that we do. The typical paradigm that we work in is called the event action paradigm, and this means that when an event happens, we calculate the next state based on that event. But if you've been working in React, Redux, even MobX, you know that this is not exactly the way things work. And the more accepted pattern nowadays is that we have to consider the current states and the events in order to determine what the next state is. But that's also not adequate, because how do things happen in the app? We have to have effects. And so we need a better way to model these sorts of side effects in our app. So let's take a look at a code example real quick. You could imagine this in any framework that you work with, whether it's React, Vue, Angular, Svelte, whatever. But let's say that you have an event handler which is on search. And this search takes in a query, and the query calls the Flickr API, and then once it receives the data, it sets it to the state. So we see that, that we have a problem, just like we saw on the button, is that we don't have a way of showing that it's loading. So the typical solution for this is we have what's called a Boolean flag. And so we set loading to true. And then after we get the data, then we set loading to false. But there's another problem with this too. Now we have to manage what happens if there's an error. So if an error happens when we're trying to call the API, we have to set the error Boolean flag to true, and we have to set loading to false again. But then what if the user wants to retry? Well, then if they do on search again, we have to make sure to set that error Boolean flag to false and set the loading flag back to true. And then what if we want to cancel the current promise? Then we have to have some sort of cancellation flag. And can you all see that? Here, I'll zoom in for you. You have to have some sort of cancellation flag that lets a promise know that the promise was canceled. And so there's a whole lot of problems with that. I don't even know what that says, to be honest with you. This is known as the bottom-up approach. And the bottom-up approach happens when we have some sort of event listener and we stuff all of the application logic inside of that event listener. So I'm going to give you a preview into what I'm going to advise for the rest of this talk, is that your event listeners should only be 1 to 2 lines at most. It doesn't matter how complex your application is. You should not have logic in your event listeners. You should send an event, delegate that event somewhere else, maybe do events.prevent propagation or whatever it is. But you should not have all this logic inside of your event handlers. So this bottom-up approach is typically how we start coding apps, and it is a source for a lot of complexity. And so there's a problem with this event handler-driven bottom-up code. First of all, it's difficult to test. And it's difficult to test because all of the logic in our app lives inside each one of those event handlers. This makes it very difficult to understand the app, whether you're a developer or a user, just because the developers cannot be too sure where the features or where the app logic lies because it's spread out all over the place, and the users might run into edge cases where they're not sure, is this the way the app is supposed to work? This means that your code will contain bugs for sure. It's just a mathematical, definite probability because you have so many different states everywhere. And so this makes your code difficult to enhance, where I'm sure you've all run into the situation where if your boss or someone tells you, hey, we need to add this feature, it's a small little thing, it'll be easy, right? And then you realize that that feature actually affects so many different parts of the app. And in fact, features make it worse. Because the more features you add, the more combinatorial complexity that your app now contains. So how can we better model the behavior of user interfaces in a declarative way and in a way that's easy to understand? It turns out the solution has been around for over half a century, and it's called finite state machines. And there's also something called statecharts, which we'll talk about a little bit later. Now, if you go to Wikipedia, there is a mathematical definition of a finite state machine, which says that it is a tuple of 5 parts, so it's a quintuple. A finite state machine has 5 parts. The first part is the initial state. So all finite state machines need to start somewhere. And so in this example, we have an initial state for a promise in which it's idle, nothing's happening yet. Finite state machines also have an alphabet, which is the mathematical term for it, but it is the finite number of states that you could be in. And so the rule with finite state machines is you could only be in one of these states at any given time. So a finite state machine also has a finite number of events that could happen in the state machine, and these events could come from anywhere. They could come from within the machine, they could come externally, they could come from other services, but the point is that the machine reacts to these events. And when it does react to these events, it transitions between states. So if you're in the idle state and you have a fetch event, now you go from idle to pending on that fetch event. And so these transitions, of course, are also finite, and they determine the behavior of the machine. And so you also have a finite number of final states, and these are states that indicate that the processing of the machine is done. Now, typically, applications we don't have as done because they live for the lifetime of however long the app lasts. But if you have something like a form wizard, then you could have like one final ending step, and then that indicates that it's complete. So let's take a look at our original problem, where we have a searching and we have we want to either resolve or reject it, and we want to give the user the ability to search again. So this could actually be modeled as a finite state machine, as you see here. And so we see that when we're in the idle state and we do a search, now we're in the searching state. Notice that there is no outgoing transition, or in mathematical terms, an outgoing edge from the searching state on the search event. That means if the user presses that search button many, many times, nothing's going to happen because that event is not handled in the current state. So already you are preventing an entire class of bugs that you would otherwise have forgotten. So one typical way in many languages that you would create a finite state machine is with a switch case statement. And so you're going to see no matter how you implement it, you're doing the same thing. You're defining transitions between the states and events so that you could determine what is the next state given the current state and the event. So with a switch case statement, you would first take a look at the states. In this case, it starts at idle, or in this case, it's searching. And so in that state, then you switch on what the event is. So you could sort of picture this if you do Redux. This is sort of the same as a Redux reducer. And so you switch on what the type is, and then you return the state that results from being in the current state, which is searching, and the events resolve happening. And so you get success. However, I find this very, very, very tedious to type. And the problem with that is that not only is this a lot of things to type, but you can't really go through and enumerate each of the states. And so a nicer pattern that I found a couple years ago was using objects instead. And this object is just a relational mapping between states, events, and next states. So to translate the previous example into this object, we could just look up in states the searching state, which is our current state, and then this on object contains a mapping of events to states that result from that event being performed on that state. And so, for example, if we're in the searching state, the resolve event happens. Now we're in the success state. And so this is a lot more concise than this. And I just want to emphasize that because not only is it more concise and, in my opinion, a lot easier to read, but we could take this and we could actually visualize it. So I wrote a visualizer a while ago. Let's see if this works. And so we could just copy and paste that right into our visualizer if it lets us. And so this is just JSON, so we could just put that in like that. Cool, so now we have an automatically generated visualization of our application logic. And so you could see all the different parts of the state machine over here. We have idle, searching, failure, success, with all the transitions. And the only reason this is possible is because we're defining our state machine in a declarative way. And with this, we could even simulate the state machine too, where we could, resolve, we could reject, and we could just go through each of the states. So we'll talk more about that in a little bit, but that's one of the biggest advantages that I see to using an object instead of a switch statement. So to actually make this machine work in real life, you would need some sort of function. And this function looks very, very close to our reducer that we've been using in Redux or NGRX if you use Angular, but we have the same function signature. So in this transition reducer, we have first your state, which defaults to the initial state, of course, and we have an event, which is passed in from the machine. And so what we would do would we would first look up the current state, and then we would look up the event on that state, and this should be events.type, not event. And if that event is not handled, we just return the current state. And so in these 6 lines, we're able to represent our state machine that we created here and use it within our app because we're able to tell what's the next state based on the current state. So there's another solution for this too that I created a while ago. It's called XState. And the way that XState works is it takes that exact same structure that we made, and if you wrap it in a machine, you just import machine from XState, then it's going to do the exact same thing. The difference, though, is that we have a transition method built in, and that transition, it's actually a function. That transition function takes the current state, the events that happened, and it returns the next state. And so, of course, you could use an interpreter as well. And so you could make this machine, which is just a pure object, and the machine.transition function is a pure function, and you could actually make it a live stream of events that you could imperatively send events to. So in this instance, we're interpreting the machine, and whenever a transition happens, we're logging that state. And so if we were to send the search events to this running service from the interpreted machine, then we're going to get this state object that logs a value of searching, which is exactly what we want. And it includes a lot more nice things that we'll talk about in a little bit. So one of the earliest examples I made using state machines in XState is this interaction that I saw on Dribble by a illustrator named Shear. Makes really, really awesome animations, and they're always fun to make. So this animation in particular, you could drag, you could take a bunch of states, and you could delete them, and you could edit your week and make Sunday lasts a whole lot longer, which sounds really nice. Turns out that this was a lot more complicated than I thought, and instead of having to do it like with code and with React or whatever, I sat down and I said, you know what? We should model this as a state machine, where each of the different states over here models what phase we're in. So, we could at first be in the start state, and then we could be in the selecting state where we're drawing that rectangle. And then once they're selected, two things could happen. We could either let go, and then we're back to the selecting state, or we could drag, and then we could be in the dragging state. And then depending on if we actually put the dates in the trash bin, then we could be in the disposed state. So just to show you that, there's a lot of complexity here in this simple animation. And that's why I created a state machine, because, for example, if I don't select anything, this should just disappear. If I do select something and then I click outside, it should also disappear. If I select some of the days and then let go, I should be able to resume and grab it again. So you see that the act of dragging my mouse does different things depending on what state I'm in. So dragging again over here will not show that rectangle because we're now in a different state. And so, yeah. So with state machines as well, the software bugs are made very, very clear. And the reason why is because we're able to visualize the states and transitions in our application, and we could apply graph theory principles to that as well. So take a look at this machine. We have three states. We have idle, loading, and success. So you might wonder, what exactly is wrong with this machine? And one thing we always forget is that in the loading state, an error can happen. So what happens if an error happens? If you showed this graph to someone, you could see that we don't have any transition or any outgoing edge, as it's known in graph theory, from the loading state or the loading vertex. And so we say, okay, we could add a failure state. But now, here's two little graph theory terms. We have what's called a source vertex, which only contains outgoing edges. For instance, the idle state, we have an outgoing edge from idle to loading, but no incoming edges. And we have a sink vertex. So these sink vertexes don't have any outgoing edges, which means that if we go to the failure state, there's no way to escape from the failure state. And so these could be detected, of course, using a simple algorithm that you keep track of which edges each node has and which states connect to it. And we'll talk about that in a little bit. But because we know that this is a sink vertex and that there's no outgoing transition, we know that this is a problem because our goal state is success. And because our goal state is success, we want to make the user able to transition somehow from this failure state to success. So what we could do is we could add an edge and we could allow the user to retry from the failure state back to the loading state. And now you see that we could trace a path in the graph going from idle, loading, failure, loading, success. And so we're literally setting the user up for success. So does this scale? That's a typical question when people start using state machines. They think, okay, we're going to use the state machine everywhere. I'm going to make my app a nice big state machine, and just every time I have a new state, I just add a new transition and add all the transitions that come to the state. But we get to this problem called the state explosion problem. And I encourage you to go to Wikipedia and look up state space enumeration for more information on this problem. Now, the state explosion problem, which it's a really risky thing to Google at the airport, and I shouldn't have done that while making this slide. But the problem is that when you have many states and your app has more complexity and you need to add more states, the number of transitions increases. And so when the number of states and the number of transitions increases, then you have an exponentially larger combination of states and transitions and also possible paths throughout your state machine. So this was solved in 1987 from a computer scientist by the name of David Harrell, where he wrote State Charts, a visual formalism for complex systems. And if you look this up online, there's a nice PDF with a lot of graphics that really make it easy to understand. And so it's one of the nicer research papers that I've read. But everything I'm talking to you about today is based on these very old research papers. So David Harrell made this state charts formalism, which he also called hierarchical finite state machines. And these give you a lot of nice benefits over state machines that make it easier to manage states. So for instance, we have actions. You could think of actions as side effects because that's exactly what they are. But instead of side effects just happening anywhere, we have three possible places where side effects can happen. Whenever you enter a state, which is known as an entry action, whenever you exit a state, which is known as an exit action or an on-exit action, and whenever a transition happens, such as when the search transition happens, and that's known as a transition action. You also have guards, so you could prevent transitions from happening. For example, if we're in the idle state and our query length is not greater than 0, which means the user hasn't entered a query yet, then this transition will not be chosen. And so it's useful to not use too many guards because then you're back to the Boolean flags and if-then nested conditional traps that your old application suffered from. But they are useful in small parts. And so to see this in code, if you're using XState, then for example, we have these entry actions over here, which is prefetch resources and fetch results. So anytime you enter that state, those actions are going to be executed by the interpreter, not by the machine itself. And then on this search, we could expand that search string, or that should be searching. We could expand that string into an object with a target and a conditional. That conditional is what's known as a guard, and that determines whether that transition could be taken. So this is the same thing. If context.query.length is greater than 0, there we go, then that transition will be taken. Otherwise, we stay on the same state. There's also the concept of extended state as well. And so extended state you could think of as states that doesn't necessarily fit into finite states. So in our example searching application, we have these well-defined states of we're idle, we're searching, and then we might have a success, we might have a failure, but then there's states that can't really be modeled in a finite way, such as the query. And that's because the user could type a nearly infinite number of possible queries, and we don't want to model each one of those. So instead, we put this in what's called machine context, which is just, it's a data like a states container. And so we could change those using actions as well. And so in this case, we assign the query to the events.target.value. So you could imagine that this came from some sort of a text input. So there's also the idea of hierarchy, which is nested states. And so this groups states that have common behavior and allows you to infinitely nest these states in a recursive way. And so it makes it a lot easier to deal with the state explosion problem, as we will see soon. And there's also orthogonality, also known as parallel states. And that means that when we enter a parent state that has orthogonal states right next to each other, then we're in both of those states at the same time. Now, I don't want you to think that that means that we're violating the rule of state machines where you could only be in one state at any given time, but instead it makes it easier to represent a combination of states. And there's also history states, which allow you to go to the last state that a parent state was in. And so it's also very helpful for managing how many states you're in. So let's take a closer look at hierarchical states, for instance. When we see the success and failure states over here, we see that there's a search transition that's outgoing from each one of those. And this is what's known as common behavior. And so we could group those two states in one common state, known as the search state, or whatever you want to call it. And so we could see in the search state, we could either be in success or failure. And for both of these states, when the search event happens, because they're not handled directly by each of these states, they're instead handled by the parents, we know that no matter which state we're in, we could go to the searching state. So you see how this reduces the number of transitions just barely, but it makes a bigger impact the more complex your app gets. And so now the way that we do it in XState is that we have this machine, and because this is a declarative JSON-like structure, in fact, you could declare your entire machine as a JSON object, we could infinitely nest, or well, however much your computer could handle, but we could nest each of these states inside the parent state as well. So we see that we have the success and failure state nested right inside the search state. And we could handle on the parent state that when a search event happens, we're in the searching state. So this also allows you to refine behavior, in which if you're in a state and that state eventually evolves to have more complex behavior, then the overall machine doesn't need to change. You could still have three states like idle, searching, and searched. But we could refine these states. For example, searching, we could be like searching for users. All right, now we're searching for this user. Okay, now we're searching for these users' friends. And so we could have all of these different states, but we could still be in that parent searching state. Now, orthogonal states are a different beast. Let's say that you're trying to model a text editor in which you have three buttons. You have a bold button, italics button, and an underline button. In order to represent each of the states that those could be in, even though there are a finite number of buttons, only 3, we have 2 to the power of 3, or 8 states. So you can imagine if we add something else like strike through, now we have 2 to the power of 4, or 16 possible states. And so you could see this is where state explosion happens, because we need to represent each one of these bold off, italics off, underline off, bold on, italics off, underline off, and so on. We need to represent each one of those as its own state. So instead of that, we could use orthogonal states, and this is just a visual representation of being in all of these states at the same time. So looking back at here, this does not violate the rules of what a finite state machine is. We're still in only one of these states, but it's just visually represented differently, in which each of these start in the off position, and when we toggle each one of these, they're in the on position. Now, doing this in XState is pretty simple as well. So we have a type of parallel, and so we add this to the machine just to let it know that we're not going to give it an initial state. Instead, we're going to say that every single state that's inside, we're going to be in all of them at the same time. And then we have, all of our states. In fact, I added a strike-through state, and these states are modeled right up here, where I just, I have a function that gives it the state, and so that should be toggle config bold, toggle config italics, underline, and strike-through, and we could configure each one of those states. Now, what this gives you as a state value is, instead of a string or an object with one property, it's going to give you a state value of every single one of those properties. So we could say bold is either inactive or active, and then when we toggle bold, for instance, now it turns to active. And we could see that the other states are completely untouched. And so that's a way that we could model many states at the same time, just because naturally having an object mapping of states to their state values is combinatorially represents all of the possible states that those are combined in. So I showed you a previous visualization tool that I made, but there is a newer one, and I'm actually going to update it pretty soon. And so this visualization tool actually allows you to copy and paste those machines that we saw over here, like this one or the previous one, and you can copy and paste those and put them in the tool. And so let's just go to the tool real quick. So, and you could see that over there. So this allows you to copy and paste that same exact XState code and visualize it over here. And that way, you could model your application visually and be able to verify that all of the transitions and states are exactly as you expected. So this is just JavaScript, and there's also a way of verifying state And so you could see in this sample application, whenever a promise fails, our attempts increase. And so that's just a way of modeling context. Or after a timeout, we see that goes to rejected as well. So not only are there ways of modeling state transitions, but there's also ways of modeling time as well. For example, we have this timeout set to 2 seconds, and we could say as a transition, after that timeout, go to the rejected state. And what XState handles for you out of the box is that the timeout will be canceled if we transition away from that state. So you notice that that timeout was canceled and we didn't go to the rejected state. So that's just a way where the visualizer is useful. Or, let's say that we cached this and we just go to fulfilled. We could update that machine and see our updates live. So this is the exciting part of the talk, because you might be thinking, okay, well, this is just like Redux or MobX or any of these other like NGRX, but there's a reason that I'm so passionate about using state machines and state charts, and it's because there's many other purposes than just managing your state. For example, you could use state machines for integration testing. And so I'll explain. An integration test is basically you have a unit test which tests only one specific thing, and an integration test which tests many things that are supposed to work together. So an end-to-end flow, depending on whether you're doing it in a live browser or doing it in a simulated environment such as JS DOM, could be considered an integration test, or an end-to-end test if you want, but the result is still the same in that we need to go through each state in order to get to a goal state. So let's say that we have an app with 5 states, A, B, C, D, E. We see here that in order to get to C, we must first go to the A state, then go to the B state, and then we eventually end up in the C state. So there's many different ways to go to each of these states in this diagram, and the truth is that when you are creating your apps, there's many different ways that the user could go from one state to any other state in the app. And you have to be able to manage every single one of those possibilities, because every single time that you get a bug report in your application, it's because you did not properly test that one path. But the problem is that there could be hundreds, if not thousands or tens of thousands of those paths. And this is easy to show, like using shortest path algorithms, in which we could see that we have many different possible ways to go through each of the paths. And so, for example, if you're using Dijkstra's algorithm, then you could use weights as well. In analytics, which I will talk about in a few minutes, analytics provides those weights so you could figure out what the shortest path to any state is from the initial state. And it might not always be ABC. It might be something different like ADEC. And so when we have these analytics combined with the graph, we represent the happy paths that your users are most likely to take, and so these tests could be prioritized. And of course, because these algorithms work on this directed graph, these paths can be automatically generated, which makes testing a lot easier, especially when your application changes and you need to change like the different states, or you need to add a new feature. So there's also depth first search or breadth first search, whichever one you want to use. And these algorithms are useful for finding all of the simple paths. I'm not going to go through the algorithm exactly, but it works similar to Dijkstra's algorithm, except in a simpler way, where you would visit a node, and then you would visit each one of the other nodes. And if you see that you've already visited a node from a certain path, then you've detected a cycle. And so simple paths are every path to every state without cycles. And so that's important, because if you don't want infinitely many paths, you're going to have to assume that your user isn't going back and forth between pages infinitely, because if that's the case, something is wrong with the user and not the application. But as you can see, there's many different possible paths between A and C, and there's 2 possibilities here. We have ABC, ADEC, and so on. And so this represents all of the possible user flows again, without cycles. And the reason why these are so important is because they actually reveal all of the edge cases for us. Because when the user does something unexpected, and when they do something that causes a bug, and we're like, wow, we didn't have a test for that, then that was one of those obscure paths that the user took that we didn't realize actually had a hidden bug. Now, these could be automatically generated as well. Now, the warning about this is that because we are generating not only the shortest path, but all the possible paths without cycles, that we're going to be generating a lot more paths. Now, this is very, very useful if you want to comprehensively test your entire app and every single possible way the user could do it, but it could also make your tests like an hour long to take. And so I made an example app where it's just a feedback app, and we were able to generate all of these different paths that go from like one part of the app to the other part of the app. Now, the beauty about this is that when you change the state machine in your app, these tests are also updated because it's going to find new paths through your app. There's also another area that I want to talk about where state machines and state charts are particularly beneficial. To developers, the determinism of state machines, in which not only could you be in only one state at a given time, and there is a deterministic way of determining the next state in which you're not sure that there's going to be impossible states or whatever, that determinism is very helpful to developer experience. And so is visualization as well, because you're able to see your application logic a lot clearer. Communication is also important too, because when you have those visual diagrams, you're able to talk to your designers, developers, stakeholders, project managers, and more. And so as we saw, testability also helps with not only the developer experience, but making sure that we are uncovering possible edge cases that your users might run into. But of course, we don't always have users at our disposal to test our apps and test every single edge case, which is why you could imagine that you could use simulation with these state machines in order to simulate what the user could do. And finally, you could capture analytics that track maybe not everything, but just how the users use the app. So this gets into the area of adaptive user interfaces, where we could go beyond just creating an app that works and creating an app that works well for the user. Now, there's a few steps involved to doing this. First, we create that abstract model of the application. This abstract model is what that finite state machine is. It describes what the user is going to do. Then we have transition analytics, in which we track every time a user transitions from one state to another based on an event. We identify which parts of the app are adaptive, and we use the analysis that we captured to adapt those paths in real time without having to go through development cycles. And the result is an adaptive app that responds to the user. And because we're representing our app as a directed graph, we could actually have those analytics represented in weights in that graph. So for example, let's say that 90% of users go from sign-in to success. Then we could emphasize and visualize that that is the path that's most taken. And so we could be able to use that for analytics, testing, simulation, and more. In fact, I worked at the Visual Studio, not Visual Studio, but the VS Live Share team, in which you could collaborate with developers from across the world using VS Code, Visual Studio, and have more than one person edit on the same file at the exact same time. Now, the user interface, which is Visual Studio Code, I wanted to model what was actually happening inside the app and what the users were doing, because we didn't have rich analytics into that. And so instead of littering our entire code base with like, all right, track these analytics and track these, instead, I just had them in one place, which I'm going to show you. And I used those analytics that we tracked and made this D3 visualization. So we could see that obviously most users are going to go from initializing to signing in. And then a couple things can happen. They could either do externally signing in, which means they're going to that login with Microsoft or GitHub page, or they could immediately go to signed in. And so we could see that most users are going to sign in. Now, in the sign-in page, we want to get analytics on whether more users were joining a session or sharing a session. And so we see that, as expected, those are about equal. So this is just an example of the analytics that you could uncover just by making a state machine for your application and adding those analytics. And so let's say that we're creating a sample Instagram application. We have our login page, gallery, camera, profile, and we want to see that these paths could actually be adapted. From login, we immediately go to the gallery page, but we might be thinking, what if the user has a different preference? Instead of manually picking that preference, we could measure how often or how likely a user is to go from one state to the other state. And so, for example, going to the gallery page, we see, or staying on the gallery page, we see that this is the total weight of taking those paths. But going from gallery to camera, we see that users are more likely to navigate away from the gallery page and directly to the camera page. And then, of course, the profile page is the least likely. What we could do with this information is we could see that since users are more likely to go to the camera page, we could instead adapt this transition to go from login to camera instead of login to success. And so there's many different ways that you could use this as well. Let's say that you're trying to show ads and you want to have some internal scoring mechanism that whenever a user clicks an ad, then we want to emphasize those decisions a lot more, whether the ads are interspersed or shown at the top. So if they're interspersed, then if the user scrolls away from them, then we score -1, or we could score -10 if the user scrolls away from the ads shown at the top. And this gives us a better idea of where to show the ads. Not that I recommend using state machines to show ads to users or anything, but it's just an idea. You could also use decision trees because you remember that extended state. We have that contextual data, and we could use that contextual data, such as registration date or just any details about the user, in order to make decisions within our adapted paths. And so we could, just going based on that previous state machine, we could see that based on whether they're a new user or friend count, we could decide which paths to take in that state machine and which ones to emphasize. And so these analytics become just simplified using that interpreter again. We're just putting that analytics track right inside of the interpreter. And so this becomes a single call because you represent your entire app as a state machine, and you could track analytics right in there, giving you the target, the source, which is where the person went, the event, which should be sanitized to remove personal details, and timestamps. So there's also XState/graph, which is it contains a lot of graph theory ways to represent like all of the different paths throughout your state machine. So for instance, this is getting the shortest path of your machine. You could pass the machine directly in there, and it's going to return you all of these shortest paths. So A to B, A to B to C, etc. And it does this using weights as well. Now, you could imagine the possibilities for this, where we could also use reinforcement learning or something close to it to predict the user's behavior in the application. And so the way we would do this is you would have some sort of agent that would learn based on all of the analytics that we captured, and it would learn based on the environment in which we've modeled as a state machine, and it could be able to predict how a user is going to behave in the app. So for example, we could easily model a tic-tac-toe game, as a finite state machine. But because we have all of those transitions represented in the state machine, we could enumerate through them, which gets a little bit nasty. So I don't really recommend you do this in real life. But the result is that you could create a simple AI that plays against us and is able to predict, I think this one's going to tie, where to go. So just play terribly. Okay, it won. So, that's just an example of one way that you could utilize state machines. And so basically, we take that metrics tracking. You could store it in Google Analytics, Mixpanel, or whatever, and basically get adaptive user interfaces. Now, XState also works with Redux as well, and you could add this to the dev tools, and you don't necessarily need to use XState with Redux. In fact, I recommend you use it alone, as there are some pretty big differences between XState and Redux. In 4.6, which I just released yesterday, I want to release it live on stage, but I accidentally published it, so it's out there now. We have support for actors, which is a completely different model than Redux when it comes to managing state. Instead of having one global state container, we have tiny state containers that communicate back and forth with each other. And actors can do one of three things. They could create more actors, send messages to other actors, and designate its behavior. And its behavior is defined by the state machine. So the reason that this is important is, number one, the actor model has existed since 1973. Carl Hewitt and Alan Key, invented the ideas of the actor model separately, but they came together pretty well. And it's been in use ever since. There's popular languages such as Erlang and Akka, which use the actor model. And so we're now discovering that we could use the actor model directly in our user interfaces. And so to do this in 4.6, we have this new spawn function, which spawns a new actor. And then we could send back and forth communication between those actors. There's also support for observables in the coming version, in which you could just place an observable directly in there and be able to listen to its events. Plus, an interpreted machine is also observable too, because it has that subscribe method. Now, there's a lot of great stuff coming to XState and a lot of stuff that's also released. For example, you could use XState in React with a hook, and hopefully you all are using hooks by now. But there's this use machine hook, which works exactly the same way as a reducer, except it also executes those side effects in a managed way for you. So you use machine, you pass in your machine, and you have you could declaratively represent your UI using that. And in fact, the visualizer is created using use machine as well. There's also FSM, where if you don't need those nested states, you could use FSM, which you download from XState FSM, and that gives you a very simple way using the exact same syntax to model your state machines. And it's also extremely tiny. It's less than a kilobyte gzipped, which is pretty nice. So XState has been used for more than 2 years in a bunch of places. Some of you might be familiar with Gatsby. It's used in the file watching processes there, and they actually have a pretty involved state chart because it helps manage complexity. And there's also a talk at Google Dev Summit where they used XState and the actor model in order to demonstrate how to use separate threads on the web. So you might think I'm talking about the future of state management, which I am, but all of this is nothing new. This is all based on a spec called SEXML, which is statechart XML. And there are some popular frameworks and platforms that are using SCXML today, such as Qt and Yakindu tools. And so these tools work with Java, they work with C++ and Python as well. And they've been used in embedded electronics, automotive technology, aeronautics, and more, especially for simulation. So this is the exact same spec that XState uses as well. There's many advantages to using state charts. It was used by the NASA Curiosity rover, and they cited many benefits to using it. And so that was really cool to find out. I recommend you Google this, go to state chart autocoding for Curiosity rover, and just discover there's a really nice article on all of its benefits there. There's also disadvantages to using state charts, which I succinctly represent as 3 different categories. First of all, of course, there's a huge learning curve, something that we really couldn't cover in 1 hour. Modeling requires planning ahead too, and this is a learned skill. You can't just model everything because not everything can be modeled yet, and you have to be smart about the way you model things because it turns out there's always a simpler way to model something. So there's also complexity trade-offs. If you use an FSM, if your app is not complex, then it's going to be the simplest way to go. The typical way that we create our apps using the bottom-up approach just increases linearly in complexity. With state charts, after a certain point, we see a reduction in complexity just because of the nested states, the orthogonal states, the managed transitions, and the overall simplification of our app logic. So there's a lot of really good resources to check out too, such as the World of State Charts and the Spectrum community, where we have awesome conversations all the time about state charts. And in short, I want you to make your code do more. I don't want to just have code that manages our state or does one thing or just ships it out to the customer. I want us to create code that is testable, able to be visualized, simulated, analyzed, and more. And so with that, thank you so much, Holy.js, for having me.
Thank you, David, very much. That's a really very powerful idea, and we have some questions, and I have some questions. So let's just sit down and continue our discussion. Come on.
Oh, there's a seat.
Yeah, just take a seat. So first, it all looks really, really interesting, and it maps very well to any web project. I think we can describe pretty much everything in our life using state charts, right? So
yeah,
it's not limited only to development or to only web. Yeah, so yeah, this is cool. How do we go back to practical track? And here we are talking about XState, right? Your project. So just imagine. Let's imagine we have two states.
Okay.
Greenfield project. We just start with something, and more complex brownfield project. So let's start from the first. So I have some technical task to build some web project, and I really want to use state charts. How do you recommend me to start? npm install XState. What's next?
Actually, that's not even the first step. The first step, you take a pencil, you take paper, and you start drawing out your states. You start visualizing on paper what the app logic is going to look like. And so you're going to find yourself doing a lot of erasing, doing a lot of, oh no, it should be this way, it should be that way. And then once you have your model, then you could use it within XState. And so the easiest way to think about XState is it's just an event emitter. You're listening for events, you're sending in events. So this works basically with so many different APIs that we've already used, especially Redux, where you're listening for state changes and you're able to dispatch. And so if you treat XState the same way, in a framework agnostic way, because you could use it with any framework, then it's easy to adopt into any existing app.
So what's exactly XState is? Is that state management library? Can we say like this?
In a way it is. It's a state management library that's based on the SC-XML, which stands for State Chart XML standard. And in fact, one of the big reasons I wrote XState was because I didn't want to write XML, because that's painful.
Does it also help you to visualize your state?
Yes, so anything you write in XState, and this is one huge difference from Redux, is you copy and paste that exact same JavaScript code, put it in the visualizer, and you're able to see, visualize, and edit your machine right from the visualizer.
Oh, cool. So you start with whiteboard, then you implement your machine in the code, and then you click visualize, and you can compare, right? Is that correct or not? So they should look the same. Your initial idea and what XState generated for you.
Those should look exactly the same. So if you could represent it as a directed graph on paper, then it's going to be the exact same thing in XState.
Awesome. This is really good to check ourselves. Well. What if we have project, some web application, like say medium complexity, without any sort of state management? So we are really tired by catching all these different states, all these subtle errors, hard to test, and we are choosing state management like library, and we decided to use XState. What are our steps here? Just imagine that we already have the project ready. Should we re-architecture it seriously? Not
quite yet. And so actually this is really exciting because I'm giving a talk about it in August, but the first thing you do is write tests. But you write tests by not writing tests. So here's how that goes. So you would take your application, you would model your application as a state machine on the side. Like, don't put that state machine in your application just yet. And then I have an article coming out on this, but there's a concept called model-based testing. And model-based testing alone it's 20 years old. So these are all very old concepts. And model-based testing is, instead of manually writing each test, you take this state machine model of your application and you generate, using the algorithms we talked about, generate each of the paths, and each of those paths are a series of steps that say, oh, you want to log in? Let me go through the graph. Okay, you have to fill the username, fill the password, click login, do that. But instead of manually coding that, you would figure that out with the state machine and those algorithms. And so when you use your state machine to test your application, once all the tests pass, that confirms two things. Number one, that your app doesn't have any bugs that you've tested. And number two, that you could use that state machine inside of your app. And then you would do it in the exact same way. You would replace parts of your app that were using manual state management, and instead you use this basic event emitter approach, where you're responding to events and you're sending events up.
Nice. And the third state, if we have project with, say, Redux state management, and we are unhappy because this complexity curve goes like crazy on top, and we decided to switch to XState, what could be the transition path? Maybe some recommendations.
Transition path, I see what you did there. But what you could do is not necessarily get rid of Redux just yet. Instead, you could take each one of your reducers, model those as state machines, and then you could use XState's transition function inside of there, because the transition function itself is a reducer, and what you're doing is you're given the current state, which contains more things. It contains the value, the context, actions, everything like that. But you take that current state, you take whatever event comes in, and it's the exact same syntax as Redux as well, and then it returns you the next state. So you replace your reducer logic with state machine logic without removing Redux, without removing the reducer, and soon enough you're going to see that every single reducer in your application turned into a state machine, and then you could remove Redux. So it's like a bit by bit sort of thing.
I think this is the best path ever, when you don't have to switch everything completely at one step, but just we can eat elephant by bits, right?
Right.
Cool. And a couple of questions from our attendees. Roman is asking, is there some form of prevention of infinite loops in effects in implementation of XState?
So there's not any built-in one, but that brings up a really interesting point. In computer science, we know that there's this thing called the halting problem. And the halting problem is a problem with Turing-complete languages, such as, well, every single language you use, and that means it's impossible to detect if a cycle is going to happen. Now, finite state machines and statecharts, which are finite state machines, are less powerful than Turing machines on purpose, and it is important for them to be less powerful. But what that means is you could detect infinite cycles before they happen, because you could analyze the graph and see, oh, wait a minute, there's an infinite cycle over there. And there are algorithms to do that.
Nice. And the last one, about comparison. Do you have some benchmarks, how XState compared with Redux, Mobex, whatever else?
So I don't have any performance benchmarks on that quite yet, because the algorithm, of course, it's like a with finite state machines, it's O of 1. You're just doing an object lookup. You're looking up, all right, what's my current state? What's the event? What's the next state? And so it's O of 1. Now, of course, if you use a switch statement, it's going to be a little bit faster. If you use just your normal programming, it might be a little bit faster. And so that's not entirely the concern. My concern was I want to keep it to O of 1 or O log of n. And the way I make it O log of n is when you have nested state machines, now you have to traverse that hierarchical graph, so that makes it log of n, but still as fast as it could be. With that said, I'm still working on performance optimizations. And also, with 4.6, many of you who are using Redux know that Redux is one global state. And so that means that when you modify one part of Redux, every single reducer is going to update unless you have some really smart memoization to prevent that from happening. And even then, inside of your React component, you need selectors where Redux says, hey, something changed, and your component says, hold on, let me see if the thing that I care about changed, and you have to do all of that manually. XState takes a completely different approach known as the actor model, where instead of having one global state, it's like having local state in each of your components. So by default, that means if one change happens here, or happens here, or happens here, nothing else is going to know about it, and that's because only if they care about the state of the other actors are they going to be notified. This is the exact same principle, by the way, that MobX works on. And so you learned in the last talk that Michel gave the algorithms where change detection is only based on what cares about those properties. And so in my view, it's a smarter approach than Redux, where you change one thing and absolutely everything changes. And so in that, you're going to find performance a lot better.
Awesome.
Yeah.
Thank you very much, David.
Thank you.